Hello, I'm Ricky, and I'm going to go over some control design strategies for an inverted pendulum system. First, a look at the table of contents. I'm going to give an introduction to unstable systems, go over modeling and dynamics, look at our controller design, our simulation results, and of course, a discussion and a quick conclusion. Now first, an introduction to unstable systems and the inverted pendulum. Inverted pendulum is a very simplified form of an unstable system. Inverted pendulums remain a cornerstone in control engineering because their dynamics are inherently nonlinear, open-loop unstable, and they're extremely sensitive to perturbations. This makes them an ideal platform for evaluating feedback control strategies. Their relevance extends to real-world systems, such as rocket boosters, bipedal robots, and advanced vehicle stabilization, where continuous corrective action is required to maintain equilibrium. Without active control, even small deviations can cause rapid divergence, highlighting the need for robust strategies. Prior work has explored energy-based algorithms, linear quadratic regulators, and PID controllers, but research addressing actuator saturation, aerodynamic forces, and nonlinearities beyond small angle approximations remains limited. Addressing these factors is essential for practical application. There are two main methods. One is Newtonian mechanics. Newtonian mechanics models a cart pole system by directly balancing forces and torques, capturing both translational and rotational motion with explicit physical clarity. This approach remains very common in engineering because it makes the contribution of each force immediately interpretable. The Lagrangian formulation instead relies on energy principles, expressing the dynamics in generalized coordinates and handling constraints more naturally than force-based methods. This makes it especially effective for systems with multiple coupled motion or geometric restrictions. Despite their differences, both approaches produce coupled nonlinear equations of motion. These equations are expanded around the upright equilibrium and linearized using small angle approximations to create a practical representation suitable for control design. The linearized dynamics are then converted into state space form, enabling a rigorous analysis of stability and controllability. With this structure established, modern control techniques, such as pole placement, can be systematically applied to achieve precise stabilization and performance objectives. And now a look at modeling and dynamics. As you can see, in the cart pole system, position of the pole tip is given by xp equals x plus L cosine alpha, and yp equals L sine alpha. When we differentiate these positions, we get the velocity components, which are crucial for calculating the kinetic energy of the system. Now in the middle, this is the horizontal force balance equation. This equation captures the coupling between the cart's horizontal motion and the pendulum's rotational dynamics. The rotational dynamics are governed by the bottom equation. This equation describes how the cart's acceleration affects the pendulum's angular motion. When we combine the force and moment balances, we get fully coupled second-order nonlinear equations of motion, capturing the interaction between the cart's horizontal motion and the pendulum's angular response. Nonlinearity arises from trigonometric terms and mixed products of both translational and rotational accelerations, which creates a sensitivity to initial conditions and small perturbations. Expanding the equations clarifies the contributions of rotational inertia, velocity-dependent torques, and the gravitational restoring torque. When we linearize the dynamics about the small angle upright position, we get the standard state space form x dot equals ax plus bu, with the state vector x equals theta, theta dot x, and x dot. This linear model strips away the full nonlinear complexity while preserving the essential behavior for moderate angular deviation. The resulting system retains several defining properties. It is acutely sensitive to small perturbations. It displays non-minimum phase characteristics, and it remains open-loop unstable, which necessitates continuous feedback control. The system states are defined as x1, x2, x3, and x4, where x1 represents the cosine of the pitching angle, which provides a bounded measure of angular deviation suitable for linear control design. X2 is the angular velocity. X3 is the horizontal position of the cart, and X4 is the cart velocity. This state selection ensures that both rotational and translational dynamics are fully captured, allowing the controller to simultaneously regulate the pendulum's angle and the cart's motion, which are coupled to the system's inertia and aerodynamic effects. And now a look at our controller design. This is the controllability matrix, which we constructed and we found to have full rank. This confirms that the system is completely controlled, allowing state feedback to arbitrarily place the closed-loop poles. The rank in this case is 4 because the system has 4 states, and the columns of the controllability matrix B, AB, A squared B, and A cubed B are linearly independent. What this means is that each state can be influenced by the input, ensuring that any initial state can be driven to any desired final state, which is the definition of complete controllability. Now, the closed-loop poles we chose are -2, -2.3, -2.6, and -3, and that balances fast convergence and moderate damping, while also avoiding excessive overshoot or actuator effort. These values we chose them because placing the poles further left in the complex plane speeds up the system's response, allowing it to reach the desired state quickly, while moderate spacing prevents excessive actuator demands and ensures smoother behavior. Our values reach equilibrium at about 5 seconds, whereas another simulation using -1 instead of our values for all of its poles takes about 9 seconds to fully reach equilibrium, and it fluctuates all over the place. Using this method of numerical pole placement, the state feedback gain matrix K is computed, which produces closed-loop dynamics ACL equals A minus BK. The state feedback control law U equals -KX stabilizes all system states, regulating the pendulum angle, angular velocity, cart position, and cart velocity concurrently. Now look at our simulation results. The simulation that we developed through Python and MATLAB begins with an initial pendulum angle of about 45 degrees, with the objective of stabilizing the pendulum while keeping cart motion bounded. The results show that the pendulum angle converges very smoothly to 0. The angular velocity quickly decays, and the cart position remains within about ±0.2 centimeters. All system states move steadily toward the origin without any overshoot. The angle error settles first to establish stability, while cart drift is kept minimal. The coordinated behavior reflects effective multi-objective regulation within the single input pole placement framework. Cart velocity also returns to 0, confirming that full state convergence and restoration of equilibrium. The controller manages both rotational and translational dynamics efficiently, even from a significantly disturbed starting condition. The selected pole locations provide balanced damping, yielding smooth, non-oscillatory convergence without excessive control. Now, these frames show the pendulum moving from about 45 degrees toward the vertical, while the cart travels only about 20 centimeters. This visual sequence supports numerical results, offering an intuitive confirmation of bounded, well-controlled stabilization. The cart's limited motion reflects efficient use of horizontal displacement. The controller remains balanced without excessive repositioning, which underscores the effectiveness of our pole placement design. These results highlight the necessity of real-time feedback when responding to rapid dynamic disturbances. The same control principles here underpin stabilization challenges in aerospace systems and advanced robotics. Now, discussion. The controller we developed tolerates sensor noise and moderate parameter uncertainty, though actuator saturation and unmodeled aerodynamic effects still remain challenges. Practical implementation of our controller will require addressing these limitations, incorporating robust control strategies, and performing experimental validation to bridge the gap between theory and real-world performance. Future research will explore adaptive control to accommodate varying mass or delays, extending the approach to higher-order dynamics, and incorporating aerodynamic effects which are relevant to pitching airfoils or rocket boosters. The same pole placement principles underpin rocket booster landing, where thrust vectoring plays a role analogous to cart forces. The cart pole system remains a valuable instructional model that links theoretical control concepts to mission-critical stabilization tasks. In robotic leg balancing, joint torques serve a similar function, and the insights drawn from the cart pole problem transfer very naturally to higher complexity platforms. This demonstrates the broader applicability and enduring relevance of classical state feedback control. And now, the final conclusion. In this experiment, we use Newtonian and Lagrangian modeling, state-space linearization, controllability analysis, and pole placement to enable fast, smooth stabilization of the inverted pendulum, which provides a clear, repeatable workflow for both education and practical control design. The cart pole system bridges theoretical modeling and real-world application. Developing the full state-space model and applying targeted pole placement demonstrates the close interplay between these system dynamics, control strategy, and performance outcomes. Our future work will focus on experimental validation, robust multivariable control for systems with higher order dynamics and uncertainty, and the inclusion of aerodynamic effects, such as those relevant to pitching airfoils or rocket boosters, to extend the methodology to a broader class of unstable systems, not just inverted pendulums. Thank you very much.